面拍王玉博 and he's 黄玉豪 and he's 邱崇安 and he's 陈佑君 and he's 于大佑。
Guys.
Hello everyone, we're Team Miracle. I'm Huang Yucheng, he is Liu Zhengtao, and he is Ling Chen, he is Guo Ziqun, and he is Zhang Yongzhe. Thank you.
Okay. Hello there. Both team, would you like to introduce yourself? Okay, so my name is Guo Li. I work in the department at AU, and
Good afternoon. TYPT National University.
And that's my next one. What's the fun is
okay. So let's begin. Okay. The opponent, please.
We would like to challenge problem number 12.
Number 16.
Oh, sorry, 15. We accept.
Okay. So number 15. So please, everything please write your relative names on the blackboard.
This is the problem statement. So when you strike the side of a metal ball containing some water, you can hear the characteristics, and the sound changes when the water in the ball is moving. So we are now going to explain and investigate this phenomenon. Our focus is on the frequency, the mass of water, and its rotation. Also, frequency spectrum analysis is provided in later presentation. Then we will derive an empirical equation. This is our observation. When we hit the ball, the wailing sound will release, and the water distributed unevenly. So we are curious about how those parameters affect the frequency about the ball and the sound. This is our theory introduction. Here we consider a circular trajectory on the shape, where there exists an orbital acceleration which acts as a centrifugal force, shown as equation 1. And the radius here is for some water events. And the centrifugal force caused the water to start flowing and changes its geometry, like shown in the picture, and shaping the frequencies of the ball. So on the shaken, the water surface is not perfect parabola. Higher rotational speeds or more water enhance the geometric modification, which leads to a wider frequency shift. We will mention it later. So through the finite element method, we provide a mathematical expression as shown in this equation, where this equation can have a general solution shown in this. So we want to eliminate the x in the equation, so we consider its second order derivative and substitute the known conditions, and we can have the eigenvalue omega squared equals none. So we consider this mathematical physical meanings and compare it to the previous equation. We found out that the eigenvalue is related to the natural frequency, as shown in here, its square relationship. And the eigenvector u will decide the model shape, and in other words, the sound quality. So this demonstrates the changes in mass distribution that has an evident impact on both the frequency and sound quality. And also, the frequency, after considering the positive quantum distribution, can be written at this equation, where we assume that water has a negligible impact on sniffers. We'll prove it later. And also, this equation can tell that when you increase the mass of the material, we can lead to a smaller frequency. So we define the natural frequency we use later, as the frequency and object naturally vibrates, but not driven by any external periodic force. And later on, we shall perform qualitative analysis on how the natural frequency shifts depending on relevant parameters. Figure A, B, and C shows 3 kinds of different shifts. So this is our experiment setup. We use a tuning fork hammer to hit the ball angled by the head, and the shaker is shaped in a circular trajectory. We prepare an LMS size, and its material is 304 stainless ball with the same shape and side bay ratio to further examine our theory. So the hammer consistently beats the bottom of the ball at the same point, and we make sure that before the experiment starts, the ball's tilt is no larger than 0.3 degrees to ensure its accuracy. So about the methodology, we use a spectrum, a dB frequency graph, which clearly can demonstrate the accumulation of frequency and the dominant peaks. And in the following experiments, we will record about 15 to 20 hits, and shows the peak that only exceeds roughly minus 48 dBs. And we define peaks here as the local maximum in the graph. So although ran by a machine, the spectrum still exhibits some inconsistency, like shown in the down pictures. And we think that it's possibly due to the background interferences. So therefore, we compare the background spectrum and the experimental spectrum to eliminate the unwanted peaks, like shown in the blue boxes. So in experiment 1, we consider the rotation. In this experiment, we will change the rotational frequency in units of RPM of the orbital shaker and observe the changes of the frequency on each spectral line. The relevant parameters is this, and the control variables is mass, water mass, 100 grams, and orbital radius is 1.75 centimeters. This is for the S size 100 grams. And the 1, 2, 3 here symbolize the N spectral line. And you can see that an S size has 8 lines, but in M size, only 5, L size, and only 5. So we can have a short conclusion that the higher rotational speed is, the higher frequency we get. As shown in this, we can see that the slope is positive. And smaller balls exhibit more spectral lines that are larger than 48 dB with higher frequency. So in experiment 2, we want to consider both the mass of water and ball we observe, the respective frequency on the spectrum. We consider the following equation mentioned by before. And for simplicity and comparison, we consider its ratio only. The relevant parameters is also same. We change the water mass as 50 grams and 100 grams. Rotational speeds to 0 RPM and 125 RPM. We can see that the ratio of these two is about 0.87. It's in S form, 0 RPM, 50 and 100 grams. And the similar phenomenon can be shown in 125 RPMs, N volts, and L volts, both in 0 RPMs and 125 RPMs. So we can have a short conclusion that the more water mass is, the lower frequency the spectral line will be in every conditions, different RPM and the volts sensitivity. So, and also we increase the water mass does not have a significant impact on the stiffness of the ball, or else this ratio will not be all the same, and which can be justified by the close fit of the theoretical and experimental data. So in experiment 3, we considered the ball size. So we observed the ratio of the frequency and different spectral lines to that of the first line. So we define the ratio here of the frequency of the nth line and the frequency of the first line. So the relevant parameters is here. We also consider 50 grams and 100 grams. So you can see in this graph, if we recall the experiment 2, we reach a conclusion that the frequency of 100 grams divided by the frequency of 50 grams is about 0.9, which can also be observed in this graph, because the red point and the blue point is stick together. So here is different size of ball, 50 grams frequency ratio. Blue represents 50 grams, blue represents small balls. Red represents medium, and green represents the largest. We can see that the green is high, is not stick to the blue nor the red one, and also in 100 grams. So we have a short conclusion that while water mass does not have much impact, larger balls like L size shows higher frequency ratio, which implies a more discrete peak distribution. So we here provide an analysis about frequency change. So in this analysis, we observe that the ball lets out a waving sound when extracted. And by changing the rotational speed, we investigate the phenomenon through analyzing the patterns on the spectrum. The independent variables is water mass and the size of the ball. We find that as the rotational speed increases, apart from shifting lightworks, the most dominant frequency, circled in the blue line, wider, the peaks wider. So we define wider here as the AB ratio to be larger. So we observe that within the data range we collected, the ratio between the base and the height, the approximated triangle adhering to an empirical formula, where K is not the stiffness of the ball, which we mentioned before. It's not the stiffness of the ball. So in n size 50 grams, we can see that it adheres to this fitted line about r squared is 0.95. And also we can see that in 100 grams, m size 50 grams, m size 100 grams, L size 50 grams, and L size 100 grams. We can also see this similar phenomenon. So we have a short conclusion that the higher the rotation speed, the larger AB ratio will be. And the more water mass there is, the larger K and C there will be, which implies a wider peak, because it means that if we have a larger K and C, it means that we have a larger AB ratio. So to conclude, in experiment 1, we have the conclusion that the faster the shaker rotates, the higher each frequency spectrum line will be. In experiment 2, we find out that the more water mass is in the ball, the lower each frequency spectrum line will be. In the data range, mass does not have much impact on the stiffness of the ball. And we conclude to an empirical equation in the equation 3, and it's proven in the previous presentation. As for the faster the ball rotates, or the more water mass, the more conspicuous wailing sound will be. And the larger the bowl is, the higher frequency ratio about the first spectral mass will be. And also, we use a mathematical expression of this phenomenon to demonstrate that the change in mass distribution, or that, has an evident impact on both frequency and sound quality. There are some possible deviations. We consider Doppler effects and we find it extremely small and we neglect it. And there are not technical differences of frequency between moving or stable empty bowls. And therefore, the wailing sound observed is likely due to the water uneven distribution. And the inconsistency of the bowl density, we lengthen each recording about 2 minutes to extract the best beat. So for future research, we think that texture, materials, and precision that it hits also impact this phenomenon. And we also want to derive the relationship between the water mass distribution, centrifugal force, and depth. This is our reference, and thanks for listening.
Questions?
First, can you turn to page 14? 14? Yeah, okay.
You said that you measured next page. You said that you take out a number.
Yes.
How did you measure?
How did I write downward peaks? Like downward peaks is due to the background sound. So it means that if we place the balls here and we just record it, it may have some cells.
And how can you turn to page 27?
27? Okay.
I think it's
26?
28.
28? This?
25.
All sorts of. Okay.
You said that the frequency is compared f over f0 is
This one? Okay.
So, but you said that the mass of water is small
The mass of water.
in the experiment 3.
In the experiment suite. In this experiment suite, we didn't have nothing to do with it.
Can you turn to page 7?
Okay.
6. You said that A over omega squared is constant, but in the
Time's up. Both of you have 3 minutes to prepare your talk.
miracle. I'm the opponent of Team Miracle, on which I'm going to oppose number 15 dwelling ball. First is a problem. When you strike the side of a metal ball containing with some you will hear some characteristic sound. The sound will change when the water is moving. Explain and investigate the phenomenon. So our key point is that why the phenomenon is caused and the frequency change of the ball and the mass of water. Observation. Their observation, in their observation they didn't have the okay, in their theory they use circular trajectory and change its geometry and shifting the frequency and they also the frequency is related to the natural frequency and they have 3 different and experiment they do 3 sizes of ball and the tilt is not larger than 0.3 and they have the decibel to frequency graph and the spectrum and then they change the rotational frequency and the water mass in ball size. In the conclusion they said that higher rotation lead to higher frequency and more water mass causes lower frequency and that larger ball shows when the mass of the ball is larger, the frequency is higher and the rotational speed is higher. The AB ratio is larger, and it is no impact on the stiffness of the ball. And then it's the pros and cons of their report overview. First, observation. Their cons is that it explained too fast and they didn't show the video and the sound of the ball. And then it's the theory. They explained the relation between the rotation speed but they didn't show their graph of their theory. And then it's experiment. They have 3 experiments that are ball size, water mass, and rotation. That is good, but they didn't play the sound of all these. And then there's conclusion. They have empirical formula. That is good, but the graph is there are little graph in their conclusion. Next, I'm going to invite you for the first. Can you turn to page 42? Okay. You say that. Yeah. You said that A over B is A omega squared.
Yes.
But in the theory, you said that A is proportional to omega.
A is proportional. That's a misunderstanding about our sign use. Here A is A shaker. It's not that A is just we define the A as the height and the wide peak.
And why to do? How can you put A over B to the K omega squared?
This is just an empirical formula, which means that there is no
from experiment.
Yes, we observe and we see that from experiment and through trial and errors. So no significance like physical meanings.
Why did you think A over B is near to omega squared?
Why do I think? because we have written a lot of paper, and some paper thinks that like in the series here, some paper thinks that it can be approximated to a harmonic motion, shm. So we think that it maybe has something to do with omega. So we try omega, omega squared, omega to the power of 3. And we find that the
You try many times.
yes, we do it through trials and errors.
Okay, so it is your experiment.
Yes, it's an empirical formula.
Okay. I think you did really good at the experiment and try to do this, but I think it will be better if you have some physical as well. Did you can you turn to page 33? Go back. I think it's maybe 38. 37. You said that water mass does not have much impact, but you said that water mass
Means does not have much impact in here both sides. It means the more discrete distribution. Here means the distribution of the peaks, not the value of the frequency. In experiment 2, we did discuss that the more water mass is, the lower frequency each spectral line will be in every conditions, like different RPMs for both. So we did consider the mass and the frequencies relationship. Like page 1.
The ratio
is defined in the previous page.
Yeah. Okay. So did you have the graph of the ratio? Yes.
And the what? And ratio to
the ratio to. Did you have a graph of the ratio to different ends or
like this different and ratio
Yes.
is different like it.
or like you have different and the. Do you have the graph that can show the ratio?
Ratio of like different
Of 150. Like
150 different ratio different.
do you have the graph to show the ratio?
This shows the ratio that in the second spectral line the ratio is about 1.4.
But
That we
it is the ratio and
no over one. No, we define the first spectral line of the frequency of the first spectral line. We here define that the ratio we discussed later is the nth frequency that divided by the first spectral line. Just or like and
what is the red line?
what is the red line? It means the frequency. Here is the dB, the sound, how noisy the sound is to the frequency.
So the red.
Yeah, this is just in the apps. Like if we want to examine this peak, we need to use this red line to match it, and we can see in this about 43 41 dB. We can tell that about 150 hertz that is. So that's its job.
Just
yeah, so you need to know which is frequency.
how do you define
Most dominant frequency? We do different frequency. I don't know what you mean by dominant.
How do you define
Dominant?
frequency?
You mean the peaks here? The definition of the peak here? Okay. We mentioned that we define the peak as the local maximum of this graph. You can see that in this is a concave down graph. So we define the peak as the highest point in this. And we know we can use the red line we mentioned before to know that the exact frequency of that peak.
And do you think the other peaks are bad?
Yes, we mentioned that we only considered 40 that exceeds 48 dB. Because in later experiments, we did a comparison between the background interferences and the experimental data. We found out that the background frequency is about like this. So we neglect those like the same one. You can see that about 48 inches. So this is the background frequency. And so we will not, although it's larger than 48 dB, but we will not collect it to our data. Yeah, you can see that this too is similar if you consider the coordinates.
Why?
This is circular. Yeah, here's circular. So you can see that about 48 to 42, right? But here it's about 39 to 48, like this peak. So this is actually the same, but the units here is, the intervals here is not the same. This is, yeah. Because we also mentioned in our previous experiment that we related to the largest detectable dBs in our whole experiment.
Okay, so you like okay. Why did you think the sound will change
Through time.
like you do it 15 to 20 times?
Oh, you can see that if you can, this is actually an accumulation of frequency. So we hit 15 to 20 times.
So it's
one data point.
So did you do the
We repeated each data point 12 times.
so do you think the sound will change over time, or do you think it just remains the same?
I think probably the sounds will change about the time when the time proceeds. Because we won't, if we use this graph, we know the wave of the sound. So if we do the Fourier transform, we can know that exactly which frequency to time graph.
Okay, so did you?
Yeah, we did not, because after our experiments, we used a Fourier transform and we got the graph and we found out that there's not a palpable evident differences between them. So we did not include it in our experiment, in our presentation.
Good. So, Holden, please summarize your discussion.
Okay, and then it's my summarize the first we talked about the experiment for the reporter's mass, and we thought that we had some misunderstood of the mass, and then we talked about if the sound changes through time, and the reporter said that they didn't have evidence to show, but I think they can do some experiments to their frequency change over time. And the reporter also did have some background And the
Okay, time's up. Reviewer, please press your question to both screens.
So thank you for the opponent and the reporter. After I said the opponent, do you think the stand wave will affect this phenomenon?
the step wave,
Standing wave?
second wave.
Yes.
Yes.
Okay. And how about the reporter?
Yeah, that's a good point, but actually we did not discuss the standing wave in our experiment
And
for
do you
that.
think
Yeah, we
this-
think that it will influence, but I think the standing wave will have something to do with the parameters that we discussed here. So it is just a transform, right?
So you think it will affect,
Yes.
but you can't compare your experiment observation.
No, I mean like the mass and the ball size and the frequency it rotates will impact the standing wave and also impacts the frequency.
Okay. So I have to ask them, have you think that how does your arrow got?
Which arrow?
You have mentioned that you got the arrow in your experiment. Have
Which
you?
one? This like this arrow box?
No, an arrow bar. The arrow.
Like actually which page? Or which experiment? We have three.
I mean, arrow bar.
Arrow bar this?
Yes.
We use we 2 times like plus and minus 2 standard deviations.
Okay. And okay, that's all. Thank you.
Okay. Reviewer, you have 2 minutes to prepare your report. Okay, reviewer, please take control.
I'm a reviewer from Digital Part, and the topic I'm going to introduce today is falling fall. And this is a product statement. And here's the summary of the reporter. And first, their theory, they consider the finite element method and the frequency after consideration of water distribution, and also the natural frequency. And they consider the empirical equation. And their experiment has their analysis is that they compare the frequency change, and the parameter has the rotational frequency, and which is positively correlated to the frequency. and also the size of the ball, which is positively correlated with the frequency. And the last is the water mass. And they say the more water mass and the lower frequency. And here's the overall of the reporter. First is his advantage. He had detailed discussion about experimental data and their explanation of the theory and the significant parameters. And our suggestion is that they have laid out theoretical data, which in their graph they only put their experimental data. And we think he needs more graphical demonstration, so it will be more easier to understand. And they have inadequate parameters consideration like the standing wave, which we think that it will affect the experiment. And the overall of the opponent. Firstly, his advantage is that he had logical argumentation and also a broad knowledge. And our suggestion is that he needs to be more clear and he needs more time management that when the short question time he can do extra question, not like he's trying to discuss with the reporter. And here's their discussion. The first question that he asks is the derivation of the empirical formula. And the reporter's answer is that he get it from his experiment. But our opinion is that if his theory is from his experiment, he cannot prove that his theory and the experiment is correct because his theory is from the experiment, that not a reference or somewhere else. And their second question is how to measure the peak, and he answered that it's from a red line to measure that peak. And also the reporter considered the environment, and he explained his graph. And the opponent asked the definition of the nominal frequency, and the reporter answered the highest point. And the last he asked is, will the frequency change over time? And the reporter answered yes, but he didn't consider it in his experiment. And the question I asked is that, will the standing wave affect the result of the experiment? And the reporter and the opponent both answered yes, but the reporter didn't put it in his experiment's consideration, and we think this will affect the experiment, so it should put it in the experiment. And we asked about the error bar, and we think his error is maybe from his water distribution. It's not from the tube.
Time's up.
Okay, thank you.
See? Question from Jerome?
To conclude our discussion, in our experiment, we found that the value time is graded from uneven water distribution, and we used a mathematical expression to explain this phenomenon. And also variables like rotation, mass, flow size are contained in our experiment. And as for the discussion part, the opponents want me to clarify on the error ratio, which I've already defined in our presentation. And also both opponents and reviewer have something misunderstanding of our empirical formula discussion. Like the empirical formula is from the data code, but we did not use any theoretical method to approach this formula. We only used trials and errors, and we observed that. So this has nothing to do with like who justifies who. And we elaborate. We need to after this presentation, I know that I need to elaborate on my symbols, like both opponents and reviewer have something misunderstanding. And also the reviewer talks about the standing wave effect. And in our opinion, we think that standing wave will be affected by all these three variables. So instead of thinking a standing wave as a parameter that will affect the frequency of the variable, in my opinion, I think that this is caused by these three variables. So if I get a specific rotational speed, specific mass, water, and a specific ball size, I maybe can have determine the standing wave. So this is not the relationship between them is not causation, but a bit more correlation. Thank you.
If you have a smart transform this program into a harmonic state, and the mass term is both mass plus quantum mass the stage. About K is constant. I would like to see which object or quantities correspond to K.
You mean in the you think the K
What is K?
in
Your ex-
like you mean in the empirical formula?
Yeah. You mimic that over the oscillator.
Sorry,
No. Just
Yeah.
I will.
you want to know which parameters will impact the K?
Your K.
Oh, that's a good question. We think that maybe it's like in our setup. I think it's where we hit the ball. And also, it can also be affected by the tape because we dangle off the ball. So we take the side of the ball. So maybe we hit it and the vibration of the ball will be impacted. So the K will change if we take only the side, two sides, or we fix it in 4 places.
So K is determined by the size of the ball.
Yes, we think that, but we didn't do an experiment. We can do it in further research.
The question will go to input. And then so the question is, in the problem statement, it says that you can hear a characteristic sound. Okay, so now I'm going to ask, what is the character of the sound after based on the reporter's experiences? He's starting from the component. What is the character of this sound?
I think the character is the dominant frequency.
I'm the same with the component, is the dominant frequency.
The characters we think is caused by the unevenly distributed water. Like we mentioned in our presentation, the water in the balls when rotating in a circular trajectory, the water will not be in a slope in the line. So the water mass will be unevenly distributed, and in our mathematical expression, we can see that the mass will influence the acceleration and the x gift. So after solving this equation, we can get that this eigenvalue and eigenfactor will influence the natural frequency and the sound quality. So which I conclude, I think that the characteristic in the problem statement might be determined by the natural frequency or the mode shape of the wave.
Any further questions?
Where is the K input? Is the experiment. In your opinion, where is the K?
Where's K?
And stands the
The K.
is experiment as a
Is it in the where's K?
yeah.
In the it's in the
Which one corresponds to K? Which one in your opinion?
it's after where's K in the power?
You mean like what parameters will affect the K in our empirical formula?
What? I think it's the height, the mass of the water and the pole.
From a fast baseline of the experimental time.
questions? No? Okay. So, let's prepare the score. Okay, so you please show your marks on the reporter. Starting from 7, 7, 8, 8, and 6. Okay, so for the opponent, 4, 5, 5, 5, and 5. And for the reviewer, 5, 6, 6, 6, and 5. Okay? So that concludes this stage of 5. Okay? So we have what? 10 minutes?
Yeah, we got 10 minutes break.
Oh, 15 minutes break. Okay?